Some of you have never seen a SciShow before in your lives. For those people, hi, I'm Hank. I think science is just very cool, and I'm glad that you agree with me enough to spend some of your time learning stuff with us. Some of you, on the other hand, are very familiar with SciShow, but did you all know that we have an entire SciShow channel about space? That's right, we devote SciShow Space entirely to exploring the universe outside of our own world, and if you clicked on this video, you'll probably like some of the other stuff that we have going on that channel. So let us delve into the wonders of the solar system together with some of our favorite episodes from SciShow Space. First, our world literally revolves around the sun, so it only makes sense that we begin our journey there.
When you talk about space, the sun tends to come up a lot. But even though we've talked about it before, we've never given you a proper tour of our closest star. Today, we're gonna change that. We'd have a bit of a problem sending a probe to the center of the sun. It would vaporize long before it got there, so it wouldn't get to see very much. But what if we sent the intrepid SciShow spaceship with its invincible Patreon-funded hull? Then we'd get to check out the sun up close, including the different processes going on in all of its layers. One of the first things we'd notice about the sun is that it's huge, and it's a place of extremes. It contains 99% of all the matter in the solar system, and just about all of it is in the form of plasma, a kind of superheated gas where electrons are stripped away from their atoms. Even the coolest places on the sun's surface are hot enough to melt every compound humans have ever found, created, or even predicted. And the sun is so big that if it were hollow, you could pack just under 1 million Earths inside of it. But it isn't hollow. All of that plasma is organized into layers, starting with the core, which makes light and heat. And it's very hot in there, with temperatures that probably go up to 15 million Kelvin. Pressures are about 250 billion times what you'd find on Earth's surface, making the plasma 11 times denser than lead. At those temperatures and pressures, smaller atoms start combining into larger ones in a process known as nuclear fusion, which releases a lot of energy. It's how the sun, like every other star, shines. The sun produces about 420 million billion watts of power every second. That's 750,000 times all the energy all of humanity uses in a whole year. Produced every second. The energy is released in the form of light, which flies away from the reaction in a random direction. But it doesn't just zoom straight out of the sun from there. According to most estimates, it actually takes about 200,000 years for light from the core to reach the surface. The sun is only about 4 light seconds across, so a photon of light should only take about 4 seconds to cross the entire thing, if it were an empty shell. But the center of the sun is so dense that light can only travel for about 1/100th of a nanosecond before running into an atom. That's only about a centimeter in a star 140 billion centimeters across. When the light hits an atom, that atom absorbs energy and releases some of it as more light, which goes off in another random direction for another 100th of a nanosecond before it's absorbed, and then the whole process starts all over again. It's not a very efficient way to get somewhere, but eventually the light ends up at the edge of the core. Meanwhile, the energy absorbed by each atom makes it a little warmer. Once it's out of the core, light enters the radiative zone, which starts at around 1/3 of the sun's radius and keeps going until about 2/3 of the radius. There, the light just keeps running into atoms and transferring energy to them. The light and heat radiate outward from the core towards the edges of the sun, hence the name. But only about 1% of the sun's fusion happens in the radiative zone because, by this point, the temperatures, pressures, and densities are all way too low. By the time it gets to the end of the radiative zone, the plasma is about 1/10th of the temperature and 100th of the density it was at the center of the core. Most of the rest of the sun is taken up by the convective zone. At this point, instead of light mostly transferring energy directly to atoms and making heat that way, the light just kind of passes by, and atoms transfer heat to each other in a process called convection. It's the same way heat circulates in the convection oven you might have in your kitchen. Hot stuff rises and cooler stuff falls. Temperatures continue to drop across the convective zone until we reach the photosphere, the main layer you'll see if you look at the sun through a special solar telescope. The photosphere is about 5,700 Kelvin, which is way too hot for a stroll, but practically freezing compared to the 15 million Kelvin we saw in the core. And just outside that layer is one of the sun's biggest mysteries, in the form of a few wispy layers known as the chromosphere and the corona, which can be millions or even tens of millions of Kelvin. That's way hotter than the photosphere, and researchers don't really know what's heating it. It seems to contradict both thermodynamics and basic common sense. Something cold shouldn't be able to heat something warm. There are a few possible explanations. Magnetic fields in the sun might be dragging matter around and superheating it in the process, but scientists still aren't sure.
It's pretty amazing to think about how the sun shines and produces energy and generally does all of its sun things so that we can continue to do the things that we do here on Earth. But before we move any further out into the solar system, we have to talk about the first planet from the sun. It's Mercury. Reed, how does Mercury do Mercury things?
Have you ever wondered what it's like on other planets? What sights would await you on the red dunes of Mars? What it would be like to dance on Saturn? What's waiting beneath the swirling clouds of Jupiter? Yeah, lots of things would kill you before you ever found out. The heat or the cold, radiation, potentially crushing gravitation, and either a total lack of atmosphere or a miasma of poison gases. But we're learning more and more about the conditions on our celestial neighbors all the time, so it's not hard to imagine what it would be like to pay them a visit. Take Mercury, for example, the sun's closest pal. Because it's only 58 million kilometers from the sun, compared to Earth's 150 million kilometers, on Mercury the sun would appear 3 times larger than it does from Earth, and 6 times brighter. So, you know, wear sunscreen. And because it's the closest, Mercury has the shortest orbital period in the solar system, completing 1 circuit around the sun in just 88 Earth days. But as it travels around the sun, Mercury actually rotates relatively slowly. 1 full rotation, which would be 1 day on Mercury, takes about 58 Earth days. So the planet ends up experiencing roughly 3 days for every 2 of its years. It's also a cute little thing as planets go, about 4,900 kilometers in diameter. That's about 40% larger than our moon, but it's still only as big across as the continental United States. And as you headed towards the planet, you'd see that it looks a lot like our moon. Gray, rocky, and uneven. Unlike the moon though, its surface is rippled with towering ridges called lobate scarps, which were created when Mercury rapidly cooled after it formed more than 4 billion years ago. In the process of cooling, the planet actually shrank by as much as 11 kilometers in diameter, giving it an appearance that's been compared to a dried apple. As you get even closer to Mercury, you'd pass through its exosphere, a thin layer of oxygen, hydrogen, helium, sodium, potassium, and other materials, most of which have been knocked off the planet's surface by solar wind and meteoroids. And because it has no significant atmosphere to burn up any rocks flying at it from space, Mercury is also heavily cratered. One impact 4 billion years ago was so nasty, it created a crater roughly 1,550 kilometers wide, known as the Caloris Basin. It's basically the size of Texas. Now, you might well think that Mercury is the hottest planet in the solar system because it's the closest to the sun. But you'd be wrong. That distinction actually goes to Venus. Since Mercury has such a meager atmosphere, it's not very good at retaining heat, so it can get a lot colder than you might think. Daytime temperatures can reach 430 degrees Celsius, sure, but at night they drop to negative 180 degrees. That's the biggest temperature swing in our solar system. And in fact, if you were to land in the right crater on Mercury, you might even find ice. Astronomers think they've found evidence of water ice lurking at the North and South poles, where there are craters so deep that they're perpetually shadowed and cold. This water was probably delivered to Mercury by the same impacts that gave the planet its pockmarked complexion. So, one last weird thing to keep in mind if you're planning a trip to Mercury is that you'd feel a lot lighter there, but not as light as you might expect. Even though Mercury is only 40% bigger than the moon, it actually has about twice the gravitation. Standing on Mercury, you'd experience 38% the force of gravity that you'd experience on Earth, compared to just 16% on the moon. What gives? Despite its small size, Mercury is actually the 2nd densest planet in our solar system, thanks to its huge metallic core. At roughly 3,700 kilometers wide, its liquid iron core takes up about 75% of the planet's total diameter. Since it's so packed with mass, Mercury exerts stronger gravitation, resulting in a lighter step than you'd take on Earth, but not quite the bounce that you'd get on the moon.
I know that last video was supposed to be all about Mercury, but Reed did also mention another planet, the hottest planet. That prize goes to Venus, and there are a bunch more hot takes about this planet, where that came from.
Venus is sometimes referred to as Earth's sister planet. It's close by and pretty similar in size. It's thought to have been fairly Earth-like early in its history. Once upon a time, it may have had lots of nice shallow seas, a great place to form life. But it's not so nice to visit anymore. A runaway greenhouse effect caused Venus to undergo massive, rapid climate change, boiling off the seas and transforming it from what may have been a pleasant, beachy planet into a desolate nightmare complete with sulfuric acid rain. Earth's got a bit of a greenhouse effect problem too, so it seems like studying Venus could help us understand both our past and our future. Too bad, because Venus is so awful, sending missions there just isn't worth it. So we know Venus is hellish, but how bad is it really? Well, the average surface temperature is 471 degrees Celsius. Mercury is closer to the sun, but it tops out in the neighborhood of 430 degrees. Venus is hotter thanks to its atmosphere. That atmosphere is made up mostly of carbon dioxide, so it traps tons and tons of heat. And the clouds are made of sulfuric acid, and those clouds do indeed rain. Meanwhile, the atmosphere is so thick that the surface pressure is a whole 90 times greater than Earth's, which would feel like being almost a kilometer beneath the ocean, if that was something human beings could experience and survive, to make the comparison. We could try to engineer something akin to a deep-sea submersible to keep astronauts alive under the pressure of Venus's atmosphere. But that would still fall somewhere between very risky and certain death. Astronauts are brave, but they're also very smart. Smart enough that there's not a lot of motivation for human missions to Venus. But what about robots? They don't need to breathe. The USSR actually sent not one or two, but 16 robots to Venus. This was the Venera project, in which a whole bunch of probes were sent to Venus in the 70s and 80s. They did send some good data back, but the absolute toughest of the landers, Venera 13, lasted a whole 127 minutes. That was longer than its predicted lifespan of a half an hour, but still shorter than the shortest Harry Potter film, which is Deathly Hallows Part 2. We checked. At that time, it was really impressive that humans were able to build something that could survive the conditions on Venus for longer than 30 minutes. It's still impressive today. And that's because machines have their limits too. If we think of a rover or a lander as a set of instruments contained in a single package, we don't just need the packaging to survive, but those instruments too. It's kind of like building a spacecraft for humans, actually. The outside needs to be strong enough to withstand the environment, and the inside needs to be hospitable to its inhabitants. Hypothetically, we could build a lander or a rover out of something that is primarily carbon, which has a melting point of 3,550 degrees Celsius, but that's just the body, the casing. Inside that casing, we need to create the pressure and temperature conditions necessary for computers and scientific instruments to function. And while we've made lots of advances in high-temperature computing, like innovating new heat-resistant materials for circuitry, we're not ready to put a computer on Venus for a long mission just yet. Essentially, we'd have to radically rethink and re-engineer everything we know about space rovers in order to send one to Venus. And the time, money, and energy it would take to do that is just not worth the results, and not really in line with NASA's current goals. Right now, we're big into astrobiology. We really want to unravel the origins of life and probe its limits. If Venus once had life on it before its seas boiled and the air became poison, evidence of that life would be incredibly difficult to get to if it exists at all. That evidence would have to have survived billions of years of, well, Venus. And if we can't get state-of-the-art technology to last longer than 2/3 of Avengers Endgame, again, we checked, we don't have much chance of finding it in time. Space exploration is inherently risky, so exploration plans are very much about risk mitigation. And whatever interesting science might theoretically be on Venus, it's not worth investing huge amounts of energy on a mission so risky when there are other much less risky targets for exploration. Take Mars, for example. Mars is very hard to get to, but it won't immediately break your machines when you get there. And every time we go, we find new and exciting evidence for a once habitable red planet, like dry lake beds and extinct hot springs. And just past Mars is a field of more great targets: asteroids. There's a lot we want to look into there, from water to chemicals similar to ones used for life on Earth. And asteroids are comparatively easy to explore. You can't have acid rain if you don't have an atmosphere. So yes, Venus is metal as heck. But that's precisely why it's not a good target. It's too metal for us. Or rather, we are not metal enough for it. Yet.
So Venus sounds terrifying. We can keep that neighborly relationship to just like waving as we take out the trash. So if we don't have like a fantastic relationship with our neighbors, we better really like our home, Earth. Our home planet is very special because there is a lot of life here. But is it the only planet that can sustain life? Reed has an explanation for where and when life could exist on Earth and elsewhere.
When we talk about the search for life elsewhere in the universe, we almost always talk about it in terms of where. Like where other habitable planets might be, and how far they are from their stars, and whether we could ever reach them. All that stuff is fun to think about. But some scientists are investigating the issue of extraterrestrial life by asking a different question. When? Because even if life has developed on other planets, it may not have shown up at the same time as it did here. Let's start with what we know. Earth is about 4.5 billion years old, and the fossil record shows that the first hints of simple single-celled organisms appear around 3.7 billion years ago. Over time, life forms became increasingly complex, with the first signs of multicellular organisms showing up in fossils that are around 1 billion years old. Since then, life has grown in complexity at an exponential rate, creating the diversity that we see today. In fact, a pair of theoretical biologists, Alexei Sharov and Richard Gordon, recently calculated that the genetic complexity on Earth has been doubling every 376 million years. That means that today, there's twice as much unique information encoded in the genomes of living things as there was 376 million years ago, and 4 times more than 752 million years ago, and so on. And this got the scientists to wondering, what if they extrapolated their trend backward? If the genetics of living things doubled in complexity every 376 million years, then when would the very first, simplest form of life have appeared? Much to their surprise, they found that, mathematically speaking, the first genetic ancestor to all life on Earth should have existed 9.5 billion years ago, 5 billion years before Earth actually formed. Now, the scientists point out that there are explanations for this. Like, it's possible that life on Earth grew more complex more quickly in the past than it does now, which would account for their results. But still, it raises the question, what if life, as a thing, in the universe, is older than our planet itself? Sharov and Gordon aren't the only ones thinking about when life began. Astrophysicist Avi Loeb recently calculated that what we think of as the general formula for life, liquid water, chemical compounds like methane and ammonia, and a rocky planet to serve as the cosmic mixing bowl, could have all formed more than 13.5 billion years ago, as early as 10 million years after the Big Bang. At that point in time, Loeb figures there were probably some planets, most likely rogue planets, not bound to any star, formed from the cast-off debris from the very earliest stars in the universe that had already exploded. And those planets wouldn't have even needed nice, balmy orbits around a friendly star to get the spark of life out of their chemical mixtures. That's because the universe started off extremely hot and has been cooling ever since. So at some point, he says, the average temperature of the universe was in the right range for those rogue planets to have liquid water on their surface. Nutty, I know. But studies like these suggest that life could be older than we think, and that it could naturally spread from place to place around the universe, a theory known as panspermia. According to this theory, impacts could blast material off the surface of a planet, and that debris could carry with it the ingredients for life. And if it kicked out fast enough, some of that material could eventually end up on other planets. In this scenario, simple components of life from rogue planets could have been mixed in with the material that our solar system formed from billions of years ago. So, I'm not saying it's aliens. No, seriously people, I'm not saying that life on Earth was brought here by aliens. What I'm saying is that panspermia is one potential explanation for why the trends of genetic complexity that we see suggest that life on Earth could be older than the planet itself. Now, this theory doesn't explain where those components came from in the first place, and it doesn't mean that life is necessarily abundant in the universe, because a seed still needs to find fertile soil in order to sprout, right? So it could still be that life we have here on Earth is rare, maybe even unique within our larger celestial neighborhood. What these new studies suggest is just that the best question may not be, are we alone in the universe? It may be more like, Are we the first advanced life in the universe? Or are we just the most recent link in a chain of life that dates back to the early universe?
We really should appreciate the circumstances that led to our ability to thrive on Earth, because they do not happen every day or every million days. And some researchers have put a lot of thought into what it would take for those circumstances that promote human habitability to be reproduced on another planet like Mars. That process is called terraforming, and it would look a little like this.
In some ways, Mars kinda sounds like a cool place to live, doesn't it? The red soil, the craters, the dormant volcanoes, seems pretty scenic. And if you chose the right real estate, you could use one of the Viking landers as like a lawn ornament or something. But of course, you'd have to be okay with temperatures around -60, an unbreathable atmosphere, and deadly doses of radiation, which for most people are kind of deal breakers. But technology can do some fantastic stuff. And scientists who study terraforming, the science of transforming a planet to support human life, have put a lot of thought into changing these things. Turns out, with a few centuries worth of effort, we might be able to make Mars habitable for humans. But I'm not gonna lie to you, it would be really, really hard. A whole bunch of major things would have to change. Most importantly, Mars needs an Earth-like atmosphere. There are a few theories about how to create one, and they have a lot to do with the planet's history. In its younger days, about 4 billion years ago, Mars was actually pretty similar to Earth. It was warm and wet and had something of an atmosphere. That's because the Martian soil absorbed a lot of carbon dioxide and nitrogen that was floating around in the air. But then, active volcanoes recycled those materials by baking them out of the soil, so they could be absorbed again. The result of this was an atmosphere that mostly stayed put. Asteroids that kept hitting the planet helped out too, keeping it nice and warm. And back then, Mars had a magnetosphere, a planetary magnetic field that protected the atmosphere from being stripped away by solar winds. But then the planet cooled and lost its magnetosphere. There were fewer asteroid collisions and its volcanoes stopped erupting. Without all that help, Mars's surface absorbed a lot of the compounds from its atmosphere and lost most of what was left to solar winds, leaving a freezing, dry, barren world. Sounds pretty bleak, I know. But given what we know about Mars's history, with a little tweaking, we might be able to bring that atmosphere back. Basically, we need to start a massive global warming effect, something that humans seem pretty good at. And scientists have come up with 3 main ways to do it. The first and easiest way might be to just build factories that would basically turn carbon, fluorine, and sulfur in the Martian soil into greenhouse gases and pump them into the atmosphere. This would unlock one of Mars's greatest assets when it comes to warming things up, the thick layer of dry ice or frozen carbon dioxide that covers its south pole. An initial burst of greenhouse gases could cause this ice to sublime directly into vapor, releasing carbon dioxide gas that would help trap more heat from the sun, in turn releasing more greenhouse gases. But all that would take a while, and it would be tough to supply those factories with the resources they'd need. So another method might be to build giant 200-kilometer wide mirrors in space. They'd reflect sunlight onto the Martian ice caps, raising the surface temperature and releasing that carbon dioxide. If neither of those ideas worked, there's always the possibility of bombarding the planet with asteroids. In this scenario, we'd capture asteroids on the edge of the solar system and use rocket engines to propel them into Mars. The ammonia in the asteroids would act as a greenhouse gas. But each asteroid would be like a 70,000 megaton hydrogen bomb. So, aside from the obvious logistic problems, we'd have to do this way before humans were ready to set up shop there. And even then, once the atmosphere had some greenhouse gases in place, it would still need an ozone layer, a shroud of molecular oxygen that would absorb some of the sun's dangerous ultraviolet radiation. So there would have to be yet another step, where we introduce organisms like cyanobacteria or lichens, which would help enrich the soil and release oxygen that could eventually form ozone. Once the ozone layer was in place, the final ingredient for an Earth-like atmosphere could be added: nitrogen. This could be introduced by asteroid bombardments, or bacteria could extract it from the nitrogen-bearing compounds locked in the regolith, the rock layer just above the Martian bedrock. Easy peasy, mission accomplished, right? No, not quite. Mars would also need a way to hold onto its atmosphere and keep it from being stripped away by solar winds. Basically, it needs to get its magnetosphere back, which is the biggest problem with terraforming, because we really don't know how to do that yet. Earth has a magnetosphere, which we're pretty sure is formed by liquid metals in the core that create an electromagnetic field as they slosh around when the planet rotates. The same effect would happen on Mars if we could only figure out how to melt its core, which appears to be solid metal, not liquid. So if anyone has any suggestions on how to liquefy the middle of Mars, We're all ears.
Then again, what's wrong with Mars the way it is now? We can't live there, but we can still appreciate it for what it is, our slightly friendlier than Venus, but still deadly neighbor. And unfortunately, that might be as friendly as it gets for humans outside Earth. But for some examples of some less human-friendly planets, let's check out Jupiter and Saturn.
We've talked about what kinds of uncomfortable and ultimately fatal things would happen to you if you stepped out onto the surface of Mercury, Venus, or Mars. But what about the planets that don't have much of a surface to speak of? As we continue our journey through the solar system, we've reached Jupiter and Saturn, the largest of the gas giants. If your spacecraft were to venture into their atmospheres, would you ever hit anything solid? And what's the climate like in there? Not hospitable, would be putting it nicely. Jupiter and Saturn are mostly just helium and hydrogen, with a much higher percentage of the latter. Scientists think this may be because the gas giants formed early in the solar system's history, which allowed them to accumulate enormous amounts of the two lightest gases. Jupiter is 90% hydrogen, but it's also twice as massive as the rest of the planets in the solar system combined. It's so big that were it to be about 80 times larger, Jupiter would be considered a small star. Saturn has even more hydrogen, 96%, along with 3% helium. And like Jupiter, it contains small amounts of methane, ammonia, and water. Because it's so light and gassy, Saturn is 95 times as large as Earth, but only 12% as dense. So if you could somehow set up an experiment with it in an enormous celestial laboratory, you'd find that Saturn would float on water. Now, just getting close to either planet would be challenging for our theoretical spacecraft. Jupiter has the strongest magnetic field in the solar system, and its radiation belts are strong enough to cripple any spacecraft and kill any human that got within 300,000 kilometers of it. Radiation emitting from Saturn is relatively weak by comparison. But the question remains, does a surface exist on either planet? The answer is yes, but where exactly it is depends on what you mean by surface. Scientists define the surface of a gas giant as the point where the atmospheric pressure is equal to the atmospheric pressure on the surface of Earth, or 1 bar. So on the quote-unquote surface of Saturn, you'd experience clouds of ammonia ice, winds of up to 1,600 kilometers an hour, and bolts of lightning 1,000,000 times more powerful than those on Earth. At this level on Jupiter, the weather's no better, which we know because we've actually crashed a probe into Jupiter's Hart to see what was in there. On September 21st, 2003, 14 years after leaving Earth and 8 years after it began to explore the Jovian system, far enough away that it wouldn't get fried from radiation, the Galileo orbiter ended its mission by sending itself into Jupiter's atmosphere. Galileo wasn't equipped with cameras, but the spacecraft had instruments to measure weather conditions and cloud composition. Those instruments sent back data until the probe made it to 150 kilometers below Jupiter's equivalent of sea level, at which point it disintegrated. Galileo reported winds of 700 kilometers an hour as it descended through layers of ammonium hydrosulfide. And scientists were surprised by the high temperatures and density in Jupiter's clouds. The last data Galileo sent to Earth reported air pressures of 22 bars and a temperature of 151 Celsius. But what if we were able to build an unbreakable probe? Something totally indestructible that would go as far as possible into Jupiter and Saturn. Would it be able to pass right through them? The answer is almost definitely no, and this is where things get really strange. In addition to their more scientifically defined surfaces, both Saturn and Jupiter are thought to have solid or semi-solid cores, about 20 times the mass of Earth. No one's really sure what they're made of. Most guesses are that if it's solid, it's probably iron and other rocky materials. But what surrounds the inner core of both planets is believed to be a weird, dense mixture of liquid metallic hydrogen. Chemically speaking, atoms are metallic if they easily lose their outer electrons. At the center of these gas giants, the temperature and pressure are so high that scientists think electrons could be released from hydrogen molecules, essentially turning it into a liquid metal. And this is why Jupiter has such an enormous and dangerous magnetosphere. Jupiter completes one rotation every 9.9 hours, giving it the shortest day in the solar system. And the incredibly fast-spinning metal core generates electrical currents, creating a powerful magnetic field more than 7 million kilometers long. So, Jupiter and Saturn, who'd have thought that gas could be so fascinating?
Sounds like those planets are pretty gassy. Good thing they're far away from us. Caitlin, let's move past that onto the next planets.
We've come to the end of our journey through the solar system's planets, a trip in which our hypothetical explorers haven't fared too well. Death while visiting the previous 5 planets has come in the form of heat, cold, radiation, lack of oxygen, lack of any surface, and bone-crushing pressure, just to name a few. And we won't do much better on the ice giants Uranus and Neptune, the only 2 planets invisible to the naked eye from Earth, and perhaps unsurprisingly, the 2 we know the least about. Voyager 2 is the only probe to ever get close to either planet, making flybys of Uranus and Neptune in the late 1980s. And between Voyager 2's data and studies using telescopes, scientists have pieced together quite a bit. Earth and Venus are often described as twin planets, but Uranus and Neptune are the real siblings of the solar system, with their similar size, mass, and composition. Both are around 50,000 kilometers across. Both have about 15 times as much mass as Earth, and both contain roughly the same breakdown of gases. The freezing cold upper atmospheres of both planets are dominated by hydrogen and helium, which make up about 20% of the planet's masses. You'll also find plenty of methane. It's this methane that actually gives Uranus and Neptune their distinctive bluish hues. As sunlight passes through the outer layer of haze, the methane absorbs red and orange light, reflecting the bluer end of the spectrum. Dive deeper and eventually you'll hit the icy mantles. These mantles surround the cores and are made of methane, ammonia, and water. At over 1,000 degrees Celsius, it's pretty toasty in there, but the pressure is high enough to force the molecules into a slushy form of ice. Despite their similarities, there's still a lot that makes these planets different. So let's take a look at Uranus first. More than 2.8 billion kilometers from the sun and locked in an orbit that lasts 84 Earth years. Oddly enough, it's the coldest planet in the solar system, even though it isn't the farthest from the sun, with average temperatures hovering around negative 224 degrees Celsius. Usually, planets are warmer when they produce more heat than they get from the sun, but Uranus doesn't generate much internal heat of its own, so it stays cold. That lack of internal heat should mean that the planet doesn't have much by way of weather, except when the seasons change at the equinox, because that's when the equator gets the most sunlight. But those seasons don't change often. Thanks to the strangest rotational axis of any planet in our solar system, Uranus is tilted 98 degrees. The planet looks like it's spinning on its side, more like a ball rolling around the sun than a spinning top. That weird tilt means that 42 years at a time, one of the planet's poles is continuously facing the sun, while the other side is in complete darkness. That's over 4 decades of night. Astronomers believe Uranus got knocked over by a collision with a protoplanet billions of years ago when the solar system was still forming. They also think that's what messed with the planet's internal heating, and therefore its weather. The last equinox was in 2007, and scientists did notice larger weather patterns in Uranus's atmosphere. Infrared images of the planet have revealed occasional cyclonic storms with winds that can eclipse 900 kilometers an hour. Once the equinox was over, researchers expected Uranus to become boring and weatherless again, but it didn't. In 2014, observations using the Hubble and Keck 2 telescopes showed giant storms scattered across the planet's northern hemisphere, and astronomers still aren't sure what fueled them. Speaking of crazy weather, let's continue to Neptune, which is 4.5 billion kilometers from the sun. As a result, it receives 40% as much sunlight as Uranus, which you'd think would make it cold and boring. But that is not the case. There are some strange things happening on our 8th and final planet. In stark contrast to Uranus, Neptune has some of the most extreme weather in the solar system. Winds top out at more than 2,100 kilometers an hour, the fastest found on any planet, with storms that last for months and even years. Scientists believe the weather is thanks to plenty of heating from Neptune's core, and despite being nearly twice the distance from the sun as Uranus, its average temperature of negative 218 degrees Celsius makes the planet slightly warmer. It would be nice if we could take a closer look, but in these gaseous, icy outer reaches of the solar system, our options are kind of limited. And so our imaginary probe ends its tour of the solar system planets with an icy, windy plunge.
If Uranus and Neptune have each other, then why are they so blue? Oh right, methane. And I know, I hear it, it might rile some of you up to hear that Neptune is the 8th and final planet from the sun, but here is why we do not include Pluto. It looks like we are still debating whether or not Pluto is a planet. Will it ever end? This week at the 48th Lunar and Planetary Science Conference, scientists on the team of the New Horizons mission to Pluto presented their argument for why Pluto should be officially a planet again. Except this time, they went one step further. Actually more like 100 steps further. They proposed a new definition for the word planet that would not only include Pluto, but also 100 other bodies in our solar system. The IAU, or International Astronomical Union, is responsible for naming objects like planets and comets. Right now, there are 3 requirements for an object to be considered a planet. It has to orbit the sun, it has to have enough mass so that it's basically a sphere, and it has to clear other objects like asteroids or debris from the neighborhood around its orbit. According to the New Horizons team, there are problems with this definition. For one, it doesn't include exoplanets or rogue planets without a parent star because those don't orbit the sun. They also argue that since asteroids are constantly crossing through the orbits of all of the planets in our solar system, none of them technically have cleared their orbits of debris. Whether or not a planet can clear its orbit is also affected by the sun's gravity, so even an Earth-sized planet wouldn't be able to do it if it were farther away from the sun, like in the Kuiper Belt with Pluto. So the researchers proposed their own definition. A planet is a body less massive than a star that has never experienced nuclear fusion and that has enough mass to be roughly sphere-shaped. In other words, planets are round bodies with less mass than stars. They only based their definition on the qualities of the object, not how it interacts with other things, like the IAU's current definition. Still, even if the old definition is a little outdated, this new definition would add over 100 new planets to our solar system, including Pluto and Charon, but also including, like, our moon. Don't, like, start printing up your new giant planet flashcards deck just yet, though, because, like, it's not likely that the IAU will actually accept this definition, so sorry, Pluto fans. We may have learned a lot about Pluto and Charon thanks to the New Horizons mission, and we will continue to study them and lots of other really great objects in our solar system and in space, but that does not mean that they will be officially planets anytime soon, even though we are somehow still arguing about it. So if you Pluto enthusiasts do ever get your way and it's reclassified as a planet, we will have our work cut out for us in expanding this tour to include those 100 other planets. Until then, thank you for joining us on this tour of our solar system. And don't forget to check out SciShow Space at youtube.com/SciShowSpace for more extraterrestrial wonders.